research. So there we go. I have, just to comment on the format, I've really enjoyed sitting in and learning from these chalk talks over the last 2 years. And I appreciate the opportunity now to contribute, and I hope they continue in this format as long as you can do them. Of course, adding the hybrid. What I've especially enjoyed here in this group is the feeling that you all share this kind of sense of wonder and awe at what I call the engines of intelligence, and that you all revel as much as I do in putting the pieces of this immense jigsaw puzzle together. Over the last year, I've spent my own time trying to understand neural codes, and I dwell particularly on what aspects of nature correspond to the activity vectors that we use in machine learning, and what the underlying semantics are of any one neuron as a basis vector within a vector space. And of course, what the operators are within those vector spaces. Let me begin by scoping out my approach to today's subject. I chose it, basis vectors, because I suspect that we all recognize and have seen countless times in our work the importance of what I'll call judicious selection of vector space in coming to understand and solving problems that in any way involve differential equations.
Sorry, Gordon, it seems we have a small issue with the screen. I can see it, but it seems that other people are not able to see it. Like it does.
Yeah, it says he started screen sharing, but it's blank.
Oh, or maybe let me
Okay, I'll try screen sharing again.
There it is.
Okay, great.
Okay, perfect. Sorry.
So I was saying that I chose the topic of basis vectors because of the importance of vector spaces understanding at any fundamental level, understanding and solving problems. I also think we subscribe, all of us, at some level to this fundamental equation, describing neuron network activity and how neurons interact with each other. In machine learning, we're able to think separately about inference mode and learning mode. I often separate the behavior of natural systems in a similar fashion. There are 3 core issues, though, that have drawn my attention over the past year that have emerged from this fundamental model and that I haven't seen addressed in the literature. And I'm hoping we can have a deeper discussion about this. I'd like to see whether any of these actually rise to a first order issue as we compare models with biological systems. The common theme of these 3 is how a neuron's signal is interpreted by its target neurons, especially when a neuron seemingly changes coding schemes in the middle of sending signals. These issues are, 1, how neurons which seem to encode on 2 separate axes independently are transduced by their targets, whether there are postsynaptic demultiplexers, and if so, what is the nature of those demuxes? Second, how do target neurons deal with remapping and new codes in tuning curves? And then third, how are the sequence codes of hippocampus decoded? In trying to understand these 3 basic issues, I'm going to outline 2 themes of thought. Theme 1, patterns of thalamocortical activity suggest that we add 2 vector spaces in order to model them properly. 1, a vector space to cover phasic activity of neurons, distinct from tonic activity. And then 2, calmodulin, calcium ion calmodulin levels within dendritic spines. The second theme is that there is strong evidence the hippocampus exports data that is specifically coded as firing sequences. Also, separately, that whether or not a neuron is included in an engram can be modulated by managing the resting membrane potential of that neuron. I'm going to walk through how these 2 pieces of evidence suggest that we should be dividing signals from the hippocampus basically in the hippocampal neocortical dialogue, into two classes. The first class is data path signals, which encode the sequences within each phase of the clock, data clock, theta wave, soon to be theta clock. And then second, a collection of control signals, which separately manage and address cell susceptibility. Now, these two themes are interrelated. Outbound packets from the hippocampus, specifically the sharp wave ripple packets, project onto neurons whose dendritic spines inhabit that calcium calmodulin space that I described originally with the thalamocortical activity projections. And that calmodulin space is ultimately what mediates synaptic weight changes. So let's talk about thalamocortical vector space. Every time I read the phrase thalamic relay neuron, bells go off inside me. It is very unlikely that a biological entity like a relay neuron would be so conserved throughout evolution if all it did was retransmit a signal. Something else is going on in the thalamus, something that is worth replicating in, as far as I know, every vertebrate. So what is this transfer function? The thalamus has long been known to have two separate modes of transmission, phasic and tonic. The activity that I've chosen to illustrate here, it's actually in vitro data showing the response patterns to injected current. And you can see this happens to be from Murray Sherman's article in Scholarpedia about the thalamus. You can see in A what the tonic mode looks like. Basic resting membrane potential minus 59 degrees, minus 59 millivolts. In A is the tonic mode, most commonly seen in wakefulness. And this happens to be an in vitro prep of a lateral geniculate neuron, nucleus neuron that would communicate normally incoming retinal ganglion activity, itself a transduction of light according to a tuning curve, more or less. In B, though, we see the same neuron's response, probably as it would be during sleep, in a period of hyperpolarization, demonstrating bursting. Before going through two phases, you can see the two phases of after hyperpolarization before getting back down to its baseline of about minus 70 millivolts. Question. You and I see these as different. Do the target neurons recognize these as semantically distinct? And if not, if so, does the received activity belong in a different vector space? So my first proposition is that these are indeed separate vector spaces. We could consider hyperpolarization, this shift from minus 59 down to minus 70 due to some particular channel current. We could consider this hyperpolarization as an operator on the incoming activity space from the retina, or an operator on the weight matrix itself, making it more, it makes it look like a high pass filter and possibly a time derivative over a certain range. If you look at Sherman's original language, it even evokes the concept of a time derivative. He says something like, the tonic firing is almost linear in response to the input, whereas burst firing resembles a step function. So the received signal by these thalamocortical neurons is either retinal activity or possibly the time derivative of retinal activity. The natural follow-on questions, of course, are what transduces these signals? Can they be demultiplexed? Is there a mechanism for demultiplexing? And the answer is yes. This screen illustrates how the signals can be demultiplexed and what the output streams are. Thalamic relay neurons, and yes, I said relay and bells went off, are glutamatergic. And so their signals are transduced by AMPA and NMDA type glutamate receptors, co-located on the postsynaptic synapse. These two classes of receptors have significantly different behavioral characteristics, both in time course and in substrate, that are useful for demultiplexing. First, the NMDA type receptor has a long time course, and AMPA receptors a short time course, varying by over an order of magnitude. Secondly, NMDA mediates a large calcium ion influx, which reasonably rapidly binds to calmodulin and has a long time course also. I've pulled a graph from one study showing how calmodulin activation by calcium is modulated separately by precedence with action potential and EPSP. But also the point is that the duration is on order hundreds of milliseconds. So it outlasts any one action potential by a couple orders of magnitude. So every incoming signal is transduced into two postsynaptic signals, membrane potential or electrophysiological signal, and calcium ion. One a rapid action potential, and the other a long-lasting calmodulin ghost. I'm going to use that phrase again later. The difference in receptor time constants is enough, again, AMPA rapid, NMDA slow, that they allow incoming signals to be parsed differently according to frequency band. The NMDA time constant is long enough to act as a low-pass filter, i.e. a leaky integrator, and so presents different calcium ion profiles based on leaky integration of either tonic or phasic signals. So at any moment in our model, the postsynaptic dendritic spines, calcium and calmodulin levels represent an integrated history of the active communication action potential or membrane potential space. These two postsynaptic signals will manifest differently depending on tonic or bursting inbound signals. So we already know how to use action potential and neuron activity as an activity vector in our neural net models. These feed every model we've used, more or less, that we make of neuronal activity. So I have to ask, what's the use of a collection, these calcium calmodulin activities, ghosts, what's the use of a collection of those apparently disconnected points in the calcium calmodulin vector space that I'm proposing? Well, it's not disconnected, and in fact, it may be an important network management system. The reason it is worth modeling calmodulin ghost space separately is that there is a communication between the dendritic spines that doesn't happen via the neurons. That communication is metabolically relevant and is otherwise unrelated to tonic action potential activity. Finally, it is orthogonal to the neuron physical structure because it is along astrocyte processes that run between neurons and not parallel to them. We model synaptic activity as, very loosely speaking, postsynaptic summation of presynaptic activity. But about a third of neocortical synapses, and I think about 100% of cerebellar Purkinje cells, there's a third party, an astrocytes process. These so-called tripartite synapses, because they've got two neurons in one astrocyte, are connected along an astrocytic process to synapses that are not necessarily connected to the two neurons in the junction that we're considering. This particular study by Arizono, how long ago? Recently, 2020, looks at calcium activity in two adjacent nodes and here nodes is what they're using to describe the astrocyte connected to the pre and post synaptic neurons. It shows that there's calcium ion activity confined to at least one node in about 3/5 of synapses, and in in 2/5 of synapses, that calcium activity communicates to the second node, which is at least 1 micron away. And you can see along here, from this point here to this point is the calcium communication from one synapse to another on neurons that are otherwise unconnected, not necessarily connected. And you can also see that this is on a time constant here, where this is seconds in duration. Now, calcium communicates along these astrocyte processes, and these processes in turn form multi-astrocyte networks linked by gap junctions that connect wide areas of cortex. So there is at least one more network operating in the brain, in addition to the electrophysiological network that we spend all our time modeling. And I think it's important. Next, I'd like to continue the topic referenced a couple slides earlier, the way in which hyperpolarization, and by extension depolarization, can be viewed as a functional operator on a neuron's response properties, weight matrices. I had been talking about how a hyperpolarization operator not only pulls a cell out of likelihood to respond, but probably also changes the semantics of the messages it carries. Specifically, in that case, it was whether or not hyperpolarization could be viewed as a time derivative of a normally polarized cell. So let's take a look at what a depolarization operator does. The prep of particular relevance in examining depolarization operators is the Engram formation literature of contextual fear conditioning. There's a deep and productive body of work built on the freeze reaction of rats. Contextual fear conditioning shows an animal will respond to a signal or context, like a tone or a specific cage or structure, with a freeze reaction if it has been previously paired through training with a noxious stimulus there. There's a good review by Jocelyn and Tanagawa summarizing this work, and I'm pulling a quick review from it, and want to follow along the top line here, line A of this figure 3 from them. Their works are built on a premise that sensitizing a group of neurons renders them more likely to participate in an engram ensemble, or what's called an engram ensemble. Jocelyn's group demonstrated experimental creation and subsequent managed loss of engram function in the lateral amygdala. These purple circles show how they're able to transfect cells that they were subsequently able to manage optically. So if you look at the top, they were able to transfect purple ringed cells. Then they were able to train neurons into using the CFC, the conditioning response, train the neurons, and then they were able to ablate them functionally. So you see them going from purple. Many of the purple get red filled because they end up being allocated to an engram, and then they were able to remove cells from that engram and show that when they remove by functionally inhibiting them, optically inhibiting them, the memory, which we just look at as that little gray, their memory response diminishes. Tanagawa was correspondingly able to show that he could do a comparable experiment where he could train up an engram, and then by artificially stimulating those cells, get the trained response, the trained freeze response when not in context, in the freeze context. The importance of this work is twofold. First, it demonstrated the ability of an external signal as transfected into the cells to influence the way in which synapses change their weights. Also, it shows how the neighborhood of those cells maintained the integrity of inclusion into an engram. the key point I didn't mention was that it's not actually depolarization, it's the relative depolarization. They were able to show other work was able to show relative depolarization is the critical aspect of this. And that's obviously, maybe not obviously, that's maintained by the neighborhood. To reiterate, by increasing network sensitivity or depolarization, the cell is more likely to be included in an engram. Also, the neighborhood restricts inclusion in the engram. I want to just do a quick aside on one aspect of this that is intriguing, and that is what I call here and what I refer to later as the arbitrariness of inclusion. Let's consider all possible classes. If we think of all the cells here in that little triangle up in A1 that are possible engram cells, and let's divide them into those which get included and those which aren't included in the engram, E and call it not E. They each have projection spaces, P and I'll call them not P. The allocation that got done by sensitization also shows that neurons in P, meaning those that they were projected to in the engram, must receive an additional signal at some point in time in order to back reference their inclusion in that engram. These cells, the projected cells, are not distinct, sorry, the engram cells are not distinguished by their projections. They're distinguished by that which projects upon them. And that gets back to this issue of how cells understand or transduce signals that they get sent. I want to switch now to talk about and consider the place cell of the hippocampus, the foundation of another really robust literature surrounding the concept of engrams. There are cells in the hippocampus, and I'm sure many of you have done work in this field, so I apologize for being repetitive and superficial in coverage of this. But there are cells in the hippocampus with tuning curves that are specific to particular locations or fields of interest within a context or environment. Before I go any further, I want to say there is something that is an environmentally measured characteristic in the hippocampus called the theta wave, and it's a regular, reasonably regular depolarizing, environmentally observed wave that runs, broadly speaking, from 4 to 12 hertz. I will abbreviate it as being 8 hertz plus or minus. And yes, it is troubling for me to talk about hertz instead of megahertz and gigahertz these days, but we're down in the hertz range, 4 to 12 hertz depolarization that occurs while an animal is moving around. There are two other depolarization ranges. One is gamma, and that ranges from roughly 25 to 100 hertz, and then ripple above that from roughly 110 to roughly 250 hertz. But they do stratify in terms of low, medium, and high, low, medium, and fast. And also within each group, there are slow and fast, theta and gamma and ripple. The key point here is that the key point from my perspective is that there's one group that happens at roughly 8 hertz, and it corresponds reliably with locomotion, moving around. So these place cells, which in this chart here, we can see that Dragois characterized 5, N1, neuron 1, 2, 3, 4, and 5. They respond to a particular region or particular place, hence the name. They've got some remarkable characteristics that I'm going to collect under 3 feature sets. First, they change their tuning curves. So in here, I'm just going to call these out. We're not going to get them in depth into them, but they will change a tuning curve from one place gradually to another if there's a reward signal or if they're being trained to a reward, and these tuning curves will cluster around that reward. And then secondly, they remap. So a place cell will be in one environment, will signal a particular place in one environment, and then if the animal is put into another environment, that place cell will code for a different place. So that's one characteristic. The second characteristic is that their spikes are found and fire in sequence within cycle of theta waves based on, remember, theta waves are during locomotion. So they fire in sequence based on the places that the animal hits during its movement. And it's not just play, as in it gets there and it hits. It's a sequence coded at 8 Hertz. It includes past, present, and future. So in this chart that we're looking at right here, if you look at the theta sequence, considering where the arrow is, the animal has gone from N1 to where it is now approaching N3, and it will be at N5. And if you look at the theta sequence, it includes N1, 2, 3, 4, 5, even though the animal is not yet at N4 or N5. And then third, play cells replay. They play back when they're not near their place field. And that is when they're not near their place field and they're not moving around. Changing of tuning curves in responses to changes, environments, or rewards is important, but I'd like to focus on how the hippocampus seems to use place cells to communicate ideas of memory and sequence back to the rest of the brain. I'm going to reiterate what I just mentioned about what is called theta precession. Place cells fire sequentially within repeated cycles at about 8 Hertz. The sequence is run from where the animal was to where it is to where it will be. They fire in sequence from oldest to current to future, and then again, phase locked to an environmentally managed 8 Hertz rhythm. The evidence shows that one theta cycle encapsulates the complete concept of an animal's trajectory using the sequential ordering of place cells in phase locking. That's theta precession. And that's really interesting for coding. When theta is not running during periods of inactivity, 2 notable times, for example, after receiving a reward, or particularly during slow wave sleep, the hippocampus will replay the place cells, and again, it plays it in sequence, but this time it plays it in rapid bursts up near 200 Hertz. And it's enveloped by a particularly, this is just historically got described as a sharp wave. It's less than 3 Hertz, but if you look at what's this chart right here under where it says under forward, you can see that there's an envelope around fast ripples in between. That slow wave is slower than 3 Hertz. And the shape is clear in the slide. The activity as is shown here occurs over a background, but the synchrony of the replay within the envelope is well documented. And this one illustration I picked as exemplar. So you can see, again, looking at forward replay, you can see that there's a background of those red cells firing, but that during this burst, you can see a burst of red, blue, yellow, green, and purple in progress through that burst. The critical question to me is whether these sequence codes are some kind of control signal guiding an ensemble, or these sequences are in fact the actual packet of data in the message. Question I have again is this the fundamental code of all memory? The language that I propose the hippocampus uses to speak with the rest of the brain. In fact, the question is, does the neocortex side of the brain use one language, which we know as tuning curves, and the hippocampus use another language, which we know as sequence codes? I would like to push forward on the assumption that the sequence itself is the message, not the firing rate. The tuning curve of a place cell matters only in as much as it calls out the context, the place, and that belongs in sequence with predecessors and successors in creating an engram. The idea that the hippocampus generates sequences is not new. Bujaki and I think his name is pronounced Tinsley, and Sosa and Giacomo have all published work about this, amongst many others. But what if sequence code is in fact the primary output message of the hippocampus? Where is it being read and how? We know that cell firing history, and by extension, the animal's history, is encoded within firing sequences that we see in replay and in Precession, and that these must be used somewhere. I'm a little uncomfortable with the phrase readout, memory readout, because I think of these sequences as not being read, but actually being active and coercing. Somewhere these sequences are coercing the behavior of neurons into sequential behavior. We know some characteristics of this coercion, like when it happens, what the results are. I hope to show you that there are two coercion strategies being exercised by the hippocampus when it emits sequence codes. First, changing synapses using a high frequency band, and the other is changing activity using low frequency band. But let me walk through this. Activities in the ripple band, this is in the 200 hertz plus or minus, are used to consolidate memories outside the hippocampus to write to long-term memory during sleep. There's a long literature, dense literature about this, but I've selected this one study by Norimoto as an exemplar for two reasons. It supports the contention that consolidation can be interrupted by specifically preventing sharp wave ripples during short wave sleep. Therefore, the contention is that I support that sharp wave ripples contain the critical data package for consolidation. But it also describes how preventing sharp wave ripples also prevents a general hyperpolarization seen during shortwave sleep. And that is an interesting point for discussion. A little slower, but still in the high frequency range, in the gamma band, Fernandez-Ruiz showed that by specifically interrupting the entorhinal cortex hippocampus communication, by throwing in optogenetic inhibition at 53 hertz, they were able to interrupt memory formation. Now, this is interrupting short-term memory formation. The payload in this is also sequence-coded communication, and one that involves fast bursts pulled from theta in a mode generally describable by the phrase theta-gamma synchrony. So the sequentially coded package in ripples is used for consolidation, and in gamma for memory formation. These are both changes in synaptic strength, inviting writing synaptic changes to the neocortex during sleep or to the hippocampus for subsequent consolidation, or perhaps later use in behavior that uses that memory, but not for immediate use. Neither of these addresses the role of hippocampus and changes to real-time behavior. The hippocampus interaction with the rest of the brain for behavioral support happens during theta cycles. During theta, packages returned from hippocampus are at a slower theta frequency and amenable to coercing extrahippocampal neuronal activity as they are carried in sequence code packets. In fact, it's the medial septum management of theta that looks as though it is requesting real-time updates from short-term memory to support fast-changing environments during locomotion. Slowing down the medial septum, and this is Bujaki's paper from a couple of years ago, slowing that down leads to behavioral errors from the return path while the hippocampus continues to encode. The contribution of theta to memory creation and consolidation of gamma and ripple I just described is easily reconciled as contributory by virtue of sending real-time environmental updates through the entorhinal cortex on theta cycle onward to the hippocampus using gamma cycles. This review here by Aguilera highlights the challenge of identifying one specific theta-gamma synchrony while illustrating the point that there is sequence in the gamma wave messages that are being passed along to the hippocampus. And you can see that happening in the lower phase, that we're consolidating, we're combining the strategies of where these sit in sequential theta that happen to burst through on gamma. I referred earlier to how I envision the inference versus learning modes of biological systems. One example is here, where along this top arrow here, where I characterize the ongoing neocortical activity, by which I really mean thalamocortico-striatal activity, as operating in an ongoing behavioral mode subject to updates by some outside signal, meaning that the ongoing activity is really in the thalamocortical striatum. It is really ongoing general activity in embodying working memory without any access to recent short-term memory. So I envision it as operating in this ongoing behavioral mode, subject to updates by some outside agent, and in this case, what I love phrase from Bujaki earlier, a hippocampal appendage. The synaptic weights pushing ongoing activity are the embodiment of the long-term memory of the system. Yet, from time to time, during locomotion, environment and context change sufficiently to require updates. The medial septum, a control signal, marshes activity underlying hippocampal theta and generates that signal, the theta signal. At around 8 Hertz, we get non-long-term memory-based forecasts pushed into that stream from the hippocampus and entorhinal cortex on these theta updates. In each theta cycle, the neocortex sends along the data path, that is bulk white matter going to the entorhinal cortex from much of the neocortex, the bulk of information defining current context. And we also know forecasts. The entorhinal collects that data with forecasts based on theta polarization and packages it into a sequence code that it pushes to the hippocampus, marked here on fast time, riding the gamma clock. It also packages the return data into a packet that represents hippocampus internal and different forecasts and sends that back on theta. The entorhinal cortex recodes hippocampus space data in the return path to send to, amongst others, the accumbens retrosplenial and lateral amygdala. If we look at the fast time clocks, the hippocampus makes use of the input data packets, reclocking them on internal gamma clock for storage as short-term memory. And then finally, as instructed, when there is no theta, the hippocampus sends shortwave ripple packets back to the neocortex to write to long-term memory. So in this chart, what I've tried to show is you can see the neocortex and the entorhinal cortex cycling on theta in behavioral time, and then fast time on gamma into the hippocampus, and then shortwave ripples on even faster time to the neocortex to overwrite synapses. So I'd like to draw one theta clock cycle, and underneath a pair of electrical engineering signals for analogy to illustrate the idea of how to use a clock to frame a sequence, a data packet that is being encoded in one part of the cycle and retrieved in another. The theta cycle is a bulk measure, as described earlier. Cells are undergoing membrane potential depolarization related to the theta cycle, but they are known to precess with their spike precessions comparable to what they are measuring and re-emitting. The data packet, those cells which are firing in sequence, and here we mark them A, B, C, rely on the theta depolarization to coordinate the spike firing in phase with start markers and timing signals. As I show here, the now events are driven into short-term memory related to the trough of the cycle. So what was now A is now past, B is present, and C is in the future. The older signals in the sequence A is used to forecast signals. So one cycle represents both the forecast to B, i.e. B is forecasting A, as well as a correction that's upcoming in C to the present. We know that the ventral tegmental area coordinates with theta somehow, and that it is topographically organized behaviorally, but not somatotopically, to assist selecting theta-related information for the theta-gamma synchrony. And again, as a reminder, the VTA signal is a reward prediction error, but also related to activity selection in the accumbens. The return data via CA1 to entorhinal cortex 5A that is sequence coded, it is sequence coded, and it's looking for a target to change. I'm intrigued to find some data supporting one way or another whether the output from 5A is in fact a diff signal. I mean, as a coder, I always look for diff patch merge options and think that you know, the entorhinal 5A versus 5B and 5B versus layers 2 and 3 provides the opportunity for some kind of difference signal that would be emitted over 5A out back to the rest of the world. And then patched. So basically we have diff patched to the rest of the world, but merged in is the consolidation route. In either case, the idea is that an output signal on a runway path is timed to nudge or coerce mainstream neural activity. Are we done on time? I will go through this quickly. We're coming up on time here. There's a body of evidence showing that theta phase locked activities are able to affect behavior without affecting memory. Specifically, theta encoded sequences impact ongoing behavior, and there's a discussion of how replay or pre-play impacts navigation, largely under a rubric related to memory retrieval. The evidence is built on how theta precession data, which could be construed a pre-play or a replay, includes a forecast from the hippocampus that may or may not differ from how the neocortex projects a forecast. So if we look at how theta-driven activity outside the hippocampus affects behavioral choices, predicting that updates from the hippocampus would override neocortex. Ziegel and Wilson showed how optogenetically scrambling different phases of theta results in different behavioral outcomes. And they showed that by inhibiting theta at the peak, so-called memory retrieval phase, recency bias errors are reduced. Basically, they can eliminate really short-term memory by eliminating the retrieval from short-term memory at the peak of theta. These two other studies are important to show that in any cycle there is choice presented from the hippocampus back to the neocortex, and then finally that impacting or optogenetically stimulating place cells does alter the behavior in real time. Fast clock, on the other hand, does not act in a behavioral mode. It acts in a memory write. And in fact, my contention is that the actual signal of the gamma and ripple clocks is a specific memory write signal. And the memory that's being written is the sequence coded packet. The systematic difference is this high non-behavioral speed. And the critical points here are that the depolarization manages, the depolarization that we see in gamma manages a propensity to change synaptic strength, because this is now operating at a synaptic NMDA receptor time frame. And that specifically, again, that the calcium calmodulin ghosts in dendritic spines signal which candidate synapses are available for change based on the ABC sequence that's coming through the ripple. So gamma depolarization series is almost analogous to temperature cycles in annealing. We can look at the fast signals to manage the delta W changes in the synaptic weights and how this is coercing them by looking at the gamma controllers that are creating the depolarization triggers, the targets as the calcium calmodulin ghosts, and then addressing and enabling signals, meaning that the ventral tegmental area reward prediction error signal would select for those regions in the brain which are being allocated to that reward-based selection. And then finally, the locus ceruleus signal being able to signal attention, or that it is fundamentally time to change a synapse. The data path is along the primary pathways coming out of CA1 from the hippocampus. And I wanted to present one matrix of what a matrix of calcium calmodulin ghosts would look like on some kind of heat map. As we saw earlier in the NMDA receptor, modulation of just kind of the NMDA receptor, modulation of calmodulin in dendritic spines can do a leaky integration of fast signals into calmodulin, onto calmodulin ghosts. And what I'm trying to show in this heat map matrix is how an ABC sequence would heat map onto calmodulin ghosting. So C is the most recent, and so it's still the hottest. B on the far right shows next most active, and A is the least active over the course of one shortwave ripple burst. And we can look at fast clock signals as coercing this change of hippocampal weights, where ventral tegmental area looks like a right enable signal, and calcium calmodulin ghosting is more like a row access strobe. So let me cover summary and implications here, and thank you for listening in. First off, my contention was that thalamocortical bistability suggests a dual encoding scheme. Second, glutamate receptor dynamics demultiplex that signal into an electrophysiological space and a biochemical calmodulin vector space. And that third, the astrocytes create a network of calcium communication, which is orthogonal to neural networks and also communicates many signals that provide or are critical network management. Cell firing sequences are the underlying packet of memory. Sequences that get pulled, sequences during theta cycles pull real-time corrections from short-term memory. Gamma and ripple are memory write instructions carrying sequence codes, and that there are other control signals other control signals which use depolarization and hyperpolarization as system operators to, in depolarization, signal inclusion in a memory write, and hyperpolarization to either exclude from memory write, or to change the transform operator, the transform matrix. That synaptic weights change during these fast clock cycles, and that credit assignment is managed by calmodulin ghosting, and that weight changes may be supervised by the astrocyte network. And I want to highlight that the importance of this is that this presents an opportunity to have the network management of a neural net be done by a physically and logically orthogonal system to the network itself. And then finally, that memory and everything on the entorhinal cortex side of the brain is built on identifying differences between spike sequences. Vector spaces for short-term memory and long-term memory interactions keep changing. So work to do, and I'm looking forward to getting feedback on this. I apologize if it's been a little dense, But I'm looking forward to doing further elucidation of these specific memory write instructions, quantifying how the calcium calmodulin response occurs during ripples, doing a more complete characterization of the control signals, and then relating sequence compression to the receptor time constants. Looking to do more work on demonstrating the theta-related influence over behavior, understanding a general, diving a little more deeply into a general understanding of the polarization operators. What is an operator trying to do when it hyperpolarizes or depolarizes? I'd like to evaluate memory modes modeled as sequences. How extensive is the concept that sequence is the memory message? Can every construct, or what are the limitations to the construct of sequences or firing sequences as memory containers? And then finally, something that is really intriguing to me is to evaluate how neurogenesis in the hippocampus, adult neurogenesis, relates to adding dimensionality in understanding what goes on in sequences as they get transferred from short-term memory to long-term memory. With that, I'll say thank you very much, and look forward to your feedback.
All right, thank you, Gordon. So please ask your questions directly or in the chat, and Gordon can read them. I have questions that might not be helping your current research, but I was wondering if you have been thinking in terms of separation of time constants that people have been observing, like especially with the NMDA receptors, in terms of circuits, if there is like some that rings any alarm in your brain, like about circuit design in terms of multiplexing and having different time constants in circuit design. Oh,
I think it's when you say, I think that's what I was trying to speak to, that is a fundamental of the system, in that the different time constants between NMDA and AMPA specifically relate to parsing two completely semantically distinct signals.
Sorry, my question is perhaps ambiguous. I was wondering in terms of CMOS circuits, if there was like that bring back some memories of electronics, like in terms of multiplexing in CMOS, having circuits with like different time constants to kind of achieve the same kind of fits that
it's funny that it wasn't until starting to work on this that I actually realized that this concept, the only overlap that I've been picking up is with the idea that there may actually be control signals that operate like RAS, CAS, OE, and write enable biologically in memory writes. But I don't remember anything about what you're talking about right now.
Okay, no worries.
Yeah.
So any more
biology? Yes, just one question, if we can have a video. One question. This is Espoir. Thank you. What a great talk. I really appreciated it. One question I had was, is there any information in the reliability of these AMPA or NMDA receptors? So you mentioned there's a short time constant, long time constant, but is there any information in the reliability of the synaptic response?
So a lot of the work, so the answer is, when you say reliability, every action potential hits and releases glutamate, and there is the models are built on the probability of a response, and models are built on the the likelihood of opening or closing, and how long the closing happens. And it turns out that I think that the reliability is built into the modeling constants, so that if it happens if there's a 60% likelihood, I mean, I don't have the numbers at hand, of something opening, that reliability would be built into the bulk likelihood of opening. The intriguing problem is with NMDA, that I've seen numbers about the average opening being, one channel at any point in time, on order one channel open under some circumstances. So, and I can't remember what those particular circumstances are, but it's a wide range. And it falls into low integers where it's not a matter of, it's the law of small numbers that we're dealing with then. So.
Great, thank you.
Sure.
Any other questions? No. So good luck, Gordon, and
Thank
hope
you.
have a chance to visit Terry's lab. I think you're going to be interested by your research and model building there.
Okay, cool. Thank you very much, everybody. I enjoyed the chance.
Thank you.
Send
Bye-bye,
feedback
everyone.
if you've got it.
Thanks a lot.